Welcome to an exploration of one of the most delicious paradoxes in culinary physics, the Steamed Dumpling Juiciness Paradox. Here's the paradox. When you steam a dumpling, you're applying heat. Water should evaporate from the hot filling, yet somehow the dumpling becomes juicier, not drier. How can this be? We apply heat energy to the dumpling. Thermodynamically, we expect water molecules to gain kinetic energy and escape as vapor, yet the interior becomes more succulent. To understand this paradox, we need to meet three key molecular players: water, collagen, and gelatin. First, we have water molecules. These are simple H2O molecules that can exist as liquid or vapor depending on temperature and pressure. The phase transition equation shows that liquid water plus heat energy transforms into water vapor. Second, we have collagen. This is a triple helix protein structure found in meat connective tissue. It's rigid and tough at room temperature. Collagen forms a tight triple helix structure. This is what makes raw meat chewy and tough. Third, we have gelatin. This is what collagen becomes when heated. The triple helix unwinds into flexible random coils. At temperatures between 65 and 70 degrees Celsius, collagen denatures and transforms into gelatin. Now let's analyze the thermodynamics. We need to consider multiple competing processes happening simultaneously. First, water evaporation. This is entropy-driven. The second law of thermodynamics favors the transition from ordered liquid to disordered vapor. The Gibbs free energy equation tells us whether a process is spontaneous. Delta G equals delta H minus T delta S. For vaporization, the entropy change is positive. This favors evaporation at high temperatures. Second, collagen denaturation. This requires energy input to break hydrogen bonds in the triple helix. The enthalpy of collagen denaturation is approximately 200 kilojoules per mole. This is substantial energy. Why is the temperature range of 65 to 70 degrees Celsius so important? This is where the magic happens. Below 65 degrees, collagen remains intact and the meat is tough. Between 65 and 70 degrees, collagen transforms to gelatin. Above 100 degrees, water boils away rapidly. Steaming is perfect because it maintains the food temperature around 90 to 100 degrees Celsius. This is hot enough to denature collagen, but not so hot that water evaporates too quickly. Now here's the key to understanding the paradox. How does gelatin trap water? Gelatin forms a three-dimensional network. Water molecules become physically trapped within this network through hydrogen bonding. The hydroxyl groups on gelatin chains form hydrogen bonds with water molecules. This is represented by the dotted line indicating a hydrogen bond. Each gelatin molecule can coordinate 5 to 10 water molecules through multiple hydrogen bonding sites. Let's develop a mathematical model to quantify what's happening inside the dumpling. The total water mass equals free water plus bound water. Free water can evaporate easily, bound water cannot. The rate of free water loss is proportional to temperature, with rate constant K sub 1. The rate of bound water formation depends on gelatin concentration with rate constant K sub 2 minus a loss term proportional to temperature. Here's an important question. What determines whether the dumpling becomes juicier or drier? The answer is the ratio between the rate of gelatin formation and the rate of water evaporation. If gelatin forms faster than water escapes, net juiciness increases. We define a dimensionless ratio R. If R is greater than 1, the dumpling gets juicier. If R is less than 1, it dries out. Let's work through a concrete numerical example using a pork dumpling. At time 0, before steaming, the filling contains ground pork with collagen. We have 20 grams of pork filling. Initial water content is 60%, which is 12 grams. Collagen content is about 3%, which is 0.6 grams. After 10 minutes of steaming at 95 degrees Celsius, several changes occur. Approximately 80% of the collagen converts to gelatin. That's 0.48 grams of gelatin formed. Converting to moles, assuming a molecular weight of 300 kilodaltons, we get 1.4 times 10 to the negative 3 moles of gelatin. Each mole of gelatin combined approximately 50 moles of water through its multiple binding sites. So the bound water is 1.4 times 10 to the negative 3 times 50, which equals 0.07 moles. Converting to mass, that's 0.07 moles times 18 grams per mole, which equals 1.26 grams of newly bound water. At the same time, free water at the surface evaporates due to the heat. The mass of evaporated water is approximately 0.8 grams over the 10-minute steaming period. Now we can calculate the net change in retained water. The net change is bound water minus evaporated water, which is 1.26 minus 0.8 equals positive 0.46 grams. Remarkably, the dumpling gains 0.46 grams of retained water, even though 0.8 grams evaporated. This is the paradox resolved. But there's another layer to this paradox. Juiciness is not just about water content, it's about perception. What we perceive as juiciness is actually the rate at which water is released when we bite and chew the dumpling. In raw meat, water is trapped in rigid collagen structures. After steaming, the gelatin network is soft and releases water easily when pressure is applied. Here's the crucial fact. Gelatin melts at mouth temperature, around 35 degrees Celsius. This is why it releases water so readily. The mouth temperature is right at the melting point of gelatin. This causes the gel structure to collapse and release its bound water. There's one more effect we need to consider. What happens at the dumpling wrapper surface? The outer surface of the dumpling wrapper can reach 100 degrees Celsius, the temperature of the steam. At this temperature, the Maillard reaction occurs. Amino acids react with reducing sugars to form melanoidins, the brown compounds that give flavor. The Maillard reaction products create a semi-permeable barrier on the wrapper surface. This slows water evaporation while allowing steam to penetrate. Let's now put together the complete thermodynamic picture of what's happening. Heat enters the system. Inside, a gelatin network forms and binds water molecules. The barrier at the surface slows evaporation. The heat input equals the sum of heat for denaturation, heat for evaporation, and sensible heat to raise temperature. The heat for denaturation equals moles of collagen times enthalpy of denaturation. The heat for evaporation equals moles of water evaporated times enthalpy of vaporization, which is 40.7 kilojoules per mole. Let's calculate the energy balance for our pork dumpling example. Heat for denaturation, 1.4 times 10 to the negative 3 moles times 200 kilojoules per mole equals 280 joules. Heat for evaporation, 0.8 grams is 0.044 moles times 40,700 joules per mole equals 1809 joules. Adding sensible heat of about 1500 joules, the total heat input is approximately 3,589 joules. Here's an important question. If we're adding so much heat, why doesn't all the water just evaporate? The answer is that bound water has a higher effective activation energy for evaporation. The hydrogen bonds to gelatin must be broken first. The activation energy for bound water equals the activation energy for free water plus the hydrogen bond energy. The hydrogen bond energy is approximately 20 kilojoules per mole. This is substantial and significantly slows evaporation of bound water. There's also an osmotic pressure effect that contributes to water retention. When collagen breaks down into gelatin, it also releases free amino acids and small peptides into the filling. The osmotic pressure follows the Van 't Hoff equation, pi equals CRT, where C is the molar concentration of dissolved species. As amino acid concentration increases, the osmotic pressure draws water from the wrapper into the filling, fighting against evaporation. The amino acid concentration reaches approximately 0.1 molar after denaturation. At 95 degrees Celsius, that's 368 Kelvin, the osmotic pressure is 0.1 times 8.314 times 368, which equals 306 kilopascals. This is a significant pressure, about 3 atmospheres, that opposes water loss from the filling. Let's compare steaming to other cooking methods to understand why steaming is special. Steaming at 95 degrees gives highest juiciness. Boiling is moderate. Pan frying at 150 degrees and deep frying at 180 degrees result in much lower juiciness. At temperatures above 100 degrees Celsius, the evaporation rate exceeds the gelatin water binding rate. The dumpling dries out. The evaporation rate goes as temperature squared, while gelatin formation saturates. Above 100 degrees, evaporation dominates. One more factor: pressure. Traditional steamers operate at atmospheric pressure, but what if we increase it? In a pressure cooker, water boils at 121 degrees Celsius at 2 atmospheres pressure. This accelerates collagen denaturation, but also increases evaporation rate. The net effect depends on timing. There's an optimal time that maximizes juiciness. Too short and collagen doesn't fully denature. Too long and water evaporates. For atmospheric pressure steaming, the optimal time is typically 8 to 12 minutes for most dumplings. Different dumpling traditions have evolved different solutions to maximize juiciness. Chinese xiaolongbao soup dumplings include aspic, which is pre-made gelatin. This melts during steaming to create liquid soup inside. Japanese gyoza are pan-fried with high surface area, creating a strong Maillard barrier that traps moisture. Mongolian boos use a thicker wrapper that reduces the evaporation rate, allowing longer steaming times. Each tradition has found a different balance point in the evaporation versus gelatin formation trade-off. How can we experimentally verify this theory? Let's design an experiment. First, we measure the total mass of the dumpling as a function of steaming time. This gives us net water loss. Second, we use NMR spectroscopy to distinguish between free water and bound water based on relaxation times. Third, we perform texture analysis to measure gel strength, which correlates with gelatin network formation. Finally, trained sensory panels rate perceived juiciness on a standardized scale. What results would confirm our theory? We'd expect total mass to decrease slightly, but the fraction of bound water should increase dramatically, and perceived juiciness should increase. This dumpling paradox has broader implications for food science and cooking. First, precise temperature control is critical. The sweet spot is typically 85 to 100 degrees Celsius for many collagen-rich foods. Second, time matters as much as temperature. You need sufficient time for gelatin formation, but not so long that evaporation dominates. Third, understanding water binding mechanisms lets us engineer better texture through ingredient selection. These principles apply to braised meats, stocks, aspic, and many other dishes where collagen plays a role. Let me give you a complete mathematical summary of the paradox. The rate of change of juiciness equals gelatin formation rate minus evaporation rate, where f of t and g of p are temperature and pressure functions. The temperature function f of t is 0 below 65, linear between 65 and 70, and 1 above 70 degrees. The pressure function g of p equals 1 plus alpha times pressure minus atmospheric pressure, where alpha is a proportionality constant. The maximum achievable juiciness is proportional to initial collagen content divided by temperature. So we've completely resolved the steamed dumpling juiciness paradox. Water does indeed leave the dumpling through evaporation, as thermodynamics predicts. However, the gelatin network formation traps and binds water molecules at a faster rate than they can escape. Additionally, the gelatin network is designed to release water readily at mouth temperature, maximizing perceived juiciness. This is fundamentally a kinetic phenomenon. We're not at equilibrium. The dumpling is in a metastable state maintained by temperature. The complete picture. Heat converts collagen to gelatin. Gelatin binds water faster than heat evaporates it, resulting in increased juiciness despite water loss. Based on this analysis, here are practical recommendations for cooking juicy dumplings. Use steam rather than boiling water or dry heat. Steam maintains optimal temperature around 95 degrees. Steam for 8 to 12 minutes for standard-sized dumplings. This allows complete collagen denaturation. Don't overfill the steamer. Allow proper steam circulation for even heat distribution. Choose meat with 2 to 4% collagen content. Too little and there's no gel formation. Too much and the texture becomes gummy. Let the dumplings rest for 2 minutes after steaming. This allows temperature gradients to equilibrate.